Hello, students. Welcome to today's session of chemistry. As you all know, we have started studying 8th lesson of your syllabus, that is transition and inner transition element. Those are D block and F block elements. Of these two types, we have learned about transition elements in detail. Now, related to these elements, one more section we are going to study is extraction of metals. Now, extraction, what does it mean? Extraction, in short, we can say it is separation. Most of the metals, where they occur in nature, they occur in earth crust in the form of their salts. And these salts are naturally with non-metals because metals have natural tendency to react with non-metals to form compound. Now, in nature, as there are some non-metals abundant, so they easily react with these metals. The non-metals which are abundant in nature are oxygen, sulfur, carbon, etc. Now, metals generally occur in earth crust in the form of their salts such as carbonates, sulfates, sulfides, and oxides. And now, if we want to separate these metals from these non-metals, that separate branch is there in chemistry, and it is metallurgy. We are going to study about metallurgy later. Now concentrate on this concept. There are few metals which are non-reactive in nature. Hence, they occur in free state in nature. Which are those? Those are silver, gold, platinum. We know they are non-reactive. Hence, they occur in free state. But rest of the metals, remaining metals, as they are reactive, they will not occur in free state in nature. They will always occur in the form of compound, and which is of the type carbonates, oxides, sulfide, sulfate, as these elements are abundant in nature. Understood? Now, what is mean by mineral then? Mineral is a naturally occurring substance found in the earth's crust containing inorganic salts, solids, siliceous matter is called mineral. Now, understood by this? What is mineral? For example, take an example of iron. Do you know where we get large deposits of iron? Those occur in the states of Madhya Pradesh, Chhattisgarh, etc., where large deposits of iron mineral occur. What is the mineral then? Where the part of this which contain iron salts in abundant. So part of the earth crust where these large deposits of the mineral of particular metal observe, where from where we can separate or where we can separate out this mineral. So minerals are generally inorganic salts, but along with that they may contain clay matter, siliceous matter, that is sand, etc., along with that metal. Now, that mineral is uh, again concentrated to get an ore by removing the unwanted material. So, what is ore? Ore is the mineral itself, but which contains high percentage of the metal. And from ore, we can extract or separate metal economically. That means with few effort, we can say, with less money, less effort, because it contains high percentage of metal. We only have to use some procedure to separate out this metal, and that is called an ore. So definition of ore is the mineral which contains high percentage of the metal and from which the metal can be extracted economically is called an ore. So, mineral and ore, these are the basic concepts from which we have to separate or purify a metal. So, to make that concept more clear, let us take some examples. Now, suppose we have taken iron as an example. Then, what is the mineral of iron? The commercial name of the mineral of iron is hematite, magnetite. Again, you see the formula Fe2O3, iron oxide. That means magnetite is also an oxide. It forms a compound with oxygen, that is non-metal. So, by formula, we said it is iron oxide, but commercial name is hematite, magnetite, limonite. Limonite is again hydrated oxide, we can say, because three water molecules are there. Iron pyrites is sulfide of iron, FeS2. Siderite is carbonate of iron. These are the different minerals. But ore is hematite, the first one. Because as I told you in definition, ore is mineral itself, but where the percentage of metal is more and which can be extracted economically. That is ore. So, out of these minerals, generally hematite is used for extraction of iron. In the same way, copper has few minerals such as chalcopyrite, chalcocite, cuprite, which is oxide of copper, and of which ore is chalcopyrite. Sometimes chalcocite is also used. Likewise, zinc has minerals such as zinc blende, that is ZnS, zincite, that is zinc oxide ZnO, calamine is zinc carbonate, that is ZnCO3. Out of these three minerals, zinc blende has higher percentage, hence it is used as ore from which zinc can be separated. Now, according to your textbook, there is study of metallurgy, but as per board's decision for this year, extraction of iron is deleted from your syllabus. Only the introductional part is there for this year, hence I am going to teach that only. Now, as I told you, extraction of metal, which is done commercially from its ores, is called or is studied in the branch called metallurgy. So, different methods are used for this extraction depending upon the nature of metal and its ore. Now, there are three different branches of metallurgy which are used as per requirement. Now, first is pyrometallurgy, second is hydrometallurgy, and third is electrometallurgy. So, what does they mean? All are basically branches of metallurgy. That means there we see the extraction of metal. But depending upon the procedures they are going to use, the names are given. Now we will see one by one. First is pyrometallurgy. Pyrometallurgy, it is the process in which ore is reduced to metal. Basically, this sentence is true for every type. That is, where the ore is reduced to metal at high temperature using reducing agents like carbon, hydrogen, aluminum, etc. is called pyrometallurgy. Now, suppose example of iron. Iron is generally I told you it is oxide of iron. These all oxides are finally we have to reduce. What does it mean? We have to remove that oxygen from iron so that we get pure iron. So, to remove that oxygen, various reducing agents are used like carbon, hydrogen, aluminum at high temperature so as to get that metal in pure form is called pyrometallurgy. So, pyrometallurgy here we use high temperature. Now, second is hydrometallurgy. As the name suggests, hydro related to water. Now, here also we are going to extract metal by using a reducing agent, but From where we are going to extract metal? From the aqueous solution of their salts. Again, we have to use some reducing agent to get that metal. So this is hydrometallurgy. It is process of extracting metals from the aqueous solutions of their salts using suitable reducing agent. Now third branch, it is electrometallurgy, a process in which metal is extracted by electrolytic reduction of molten or fused metallic compound is called electrometallurgy. We have seen electrolysis of sodium chloride in the last lesson, where we learned that in electrolysis, generally reduction takes place at cathode, where electrons are accepted by the positively charged ions from the fused metallic salt compound, and that gets discharged into neutral metal. Understood? We use anode and cathode in electrolytic cell, where cathode is negatively charged. So, for example, we have seen the electrolysis of NaCl. Suppose NaCl is taken in aqueous form, because electrolysis is carried out in generally in aqueous solution, as it requires movement of electron. And then that positively charged sodium goes to cathode, where it accepts electron and gets reduced. So here generally electrolytic reduction is used, hence it is electrometallurgy. So depending upon which metal we are going to extract, the required metallurgical process is used out of pyrometallurgy, hydrometallurgy, and electrometallurgy. Understood? Now, in your textbook, there is extraction of iron given in detail. It is for CET purpose. So go and read it thoroughly so that you will understand in better way how these branches of metallurgy work. Now just introductory part is there, and that we will learn. So we will see different commercial forms of iron and difference between them. What are the commercial forms of iron? Those are cast iron, wrought iron, and steel iron. These are the three commercial forms of iron, and they have different applications, they have different combinations. What are the differences between these forms? So we will see those. So here is your table showing you differences between cast iron, wrought iron, and steel. Cast iron is hard and brittle, while a wrought iron is very soft. Steel is in between these two, that is, it is neither too hard nor too soft. Why this nature is like this? Because of the percentage of carbon in them. Cast iron contains 4% carbon, that is highest percentage of carbon, hence it becomes hard. While a wrought iron is almost pure iron containing only 0.2% of carbon, and hence it is a soft iron. While steel is in between, contains 0.2 to 2% carbon. Now, using these properties of these different types of iron, there are different applications as well. Cast iron is used for making pipes or for manufacturing automotive parts, to prepare pots, pans, utensil, etc. Cast iron is used. What is the use of wrought iron then? It is used for making pipes, as it is soft form of iron. Hence, it is used for making pipes, bars, bolts, engine bolts, etc. Well, still, it is basically used in building infrastructure. Building infrastructure is made up of steel. It is again used for making tools, ships, weapons, and in automobile parts also. So these are the different parts of, or different types of, commercial types, we can say, of iron. This much part is there for board exam. Now we will start studying inner transition elements, that means F block elements. Now what is the position of inner transition elements? These elements are located at the bottom of the periodic table in two horizontal series, out of which the upper series belong to third group and sixth period. So this square where it is written 57 to 71, out of which 57 is lanthanum. It belongs to D block. After lanthanum, 58 is cerium. From cerium to 71, that is lutetium, these 14 elements, those belong to A block. And as they come after lanthanum, they are called lanthanoids. Now, the second series or the bottom series is located in the third group and seventh period. So in this square, all the 14 elements are there. But as they can't be accommodated there, they are placed in separate row below periodic table. And first member 89 is actinum and it belongs to D block. So after actinum comes actinoids from thorium 90 to 103 lawrencium. 104 again comes in D block. Hence, these two series together form inner transition elements or F block elements. Why they are called inner transition elements? As the n minus 2 f orbitals are filled up by the electrons of these elements, and hence they are called F blocks. Our definition for P block is same. That means when the last electron enters p orbital, like that, when the last electron enters f orbital, then it is a block element. But f orbital is very much inner to that of the outer shell. Now, there are two f orbitals. One is 4f where lanthanides are there. Second is 5f where actinoids are there. And each f orbital has a capacity to accommodate 14 electrons. So 4f orbital, when they start filling up, when 6s and 5d, then comes 4f. 6s has 2 electrons, that is nth shell. N minus 1 will be 5d. As it is in the first group of d orbital may contain either 1 or sometimes 0 electrons. And then comes lanthanoids. And lanthanoid where 4f starts filling up. That means first member cerium has only 1 electron in the f orbital. And then it comes up to the last member, that is lutetium 71 where 4f 14. And again from the 72, which is a D block element, D block starts filling up. So 5d, which contains only 1 electron, now it will start filling up 2, 3, 4 like this. Understood? So as the f orbital is there located at the inner position related to D block, hence these are called inner transition elements. Understood? Okay, so let us just conclude what we learned now. Now, they are a subset of 6th and 7th period. They belong to 6th and 7th period. Since f orbital lies much inside the d orbital in relation to the transition metals, F block elements are called inner transition elements. These elements have 1 to 14 electrons in their pre-penultimate energy level. As I told you, ultimate level is nth, shall we say, nth. And that is, in case of lanthanide, it is 6s. In case of actinoid, it is 7s. So, nth shell. Penultimate shell will be d orbital, n minus 1. For lanthanides, nth shell is 6s, n minus 1 is 5d, and then 4f starts filling up. That is pre-penultimate, before penultimate. Ultimate, penultimate, and pre-penultimate. Nth, n minus 1, and n minus 2. Hence, we have to say this as inner transition element. So, these elements have 1 to 14 electrons in their pre-penultimate energy level, or that is f orbital. 0 or 1 electrons are there in the penultimate energy level, that is d orbital, and 2 electrons, they are in the outermost orbital, that is s orbital. The lanthanides are characterized by gradual filling up of 4 f orbitals, while actinides are characterized by filling up of 5 f orbitals. That means there are 14 elements filling the f orbital in each series. So this is just introduction to inner transition elements. Just read it, go through the textbook, read it again and again, listen to the video. It will make easier for you to understand these inner transition elements because they are related to transition elements itself. Now, the time for assignment. Question 1 will be define. Which are the definition you have to write? Which already I have given you: mineral, second is ore, third is metallurgy, and fourth is F block elements. Question 2 will be name the different branches of metallurgy. Give the definitions as well. Question C will be what are the differences between commercial forms of iron. Thank you.